All right, we'll give it one more minute to see if any other folks join in, and we are recording, so this will be posted to the Chicago Water Week event website here shortly as well. All right. Well, we'll get started, and hopefully we are joined by a couple more folks. But welcome. My name is Alex Johnson. I'm with Virridy, a company down in Boulder, Colorado, but working all over the United States. And I'm joined as a co-presenter by Braden Lim, a researcher from Colorado State University. Thank you all for coming, and happy Chicago Water Week 2024. Hopefully some of you have been able to enjoy it in person as well. This presentation, as you see on the screen there, is focused on wastewater utility nutrient compliance as catalyzed by a new watershed carbon methodology that Virridy and folks from Colorado State University, as well as CU Boulder, wrote and have had published this past January. And there's a couple of good examples that we'll touch on as well of utilities that are already interested in exploring the carbon mechanism to help them move towards green infrastructure for water quality goal attainment. This session is being recorded, and we will send it around to folks that weren't able to join us in person or on time, I guess. Thanks all. All right, moving to slide one, just to touch on who we are. Virridy, as I said, is based in Boulder, Colorado. It is spun out of the Global Engineering and Resilience Department at CU Boulder. But Virridy is a private and separate company whose mission is to improve the management of water resources globally. We do that through two main things. One is, as you see there, a suite of monitoring technologies that help demonstrate that water quality and water quantity objectives are either being achieved or help adapt programs to make sure they are achieved. And then a really strong expertise in environmental markets. So we will be focusing a lot on carbon credit markets, but also touching on water quality markets here in the US in this presentation. Thank you. And then looking at this presentation, we're gonna take about half an hour to 45 minutes to brief you all. Would love to have any Q&A if participants would like. And the overview is right here. We're going to touch on carbon markets to make sure everybody is aware. Certainly, as Water Week participants, you may not be aware of some of the nuances of how the voluntary carbon market works. We'll touch on the American water sector, its trajectory, some of the context there. And then pass over to Braden for a description of what his research has found in terms of the potential for GHG emissions here in the US around water utility compliance and or voluntary goals. And then I'll take it back up and just, kind of shepherd the discussion into how this would work in practice. Let me just make sure that I've got nobody hanging out in the waiting room. Looks all right. Okay. So carbon markets. So here is the voluntary carbon market kind of overview. I think for folks in the water sector, it's a little out there. It's a little different than certainly how the US water sector works. But essentially, this is, as described, a voluntary market. So there's no one government agency that regulates the carbon market. It is governed by, in the top right corner there, standards bodies, which are called carbon credit registries. Those are the organizations that have generally been around 15 or 20 years, sometimes longer, and they are full of folks whose key job is to develop methodologies, set standards, and help project developers generate credits by putting them through a process that's been agreed upon through the methodology development processes. Project developers are the ones that actually go out and generate carbon offsets. As you see in the bottom left there, a 1 metric ton of greenhouse gas emissions is equal to a single carbon credit. And a carbon credit can be sold multiple times, although generally it's a direct relationship from a project developer or an aggregator directly to a buyer. But it's a big enough market that there also are brokers. In the bottom left corner there, there's various institutions with various levels of financial backing that are able to purchase carbon offsets from project developers and then market those credits or offsets to corporate buyers at a larger scale. Those corporate buyers in the bottom right are generally global multinational companies, although more and more national companies throughout the world are also now participating in the voluntary carbon market. And those are companies that generally have set for themselves a net zero target. So they've done some look at their carbon emissions of their business, and generally those are segmented into things that they directly control all the way to emissions that are less directly controlled. Especially for those emissions that are not easy for them to abate or remove, they often look to offsets or credits to reach their net zero sustainability claims. So those are the buyers that are interested. And I would say, the dominant types of carbon credits are, as you may be aware, much to do with forestry. So avoiding deforestation, planting forests, et cetera. That's kind of the dominant nature-based credit type. And then there's also been a lot of news about technology-based sequestration, removal of carbon dioxide from the atmosphere, which is generally a lot more expensive, but obviously very robust in terms of demonstrating that the carbon emissions are real. And then moving over to the water sector. So now this is probably an area where the participants to this webinar are much more familiar, given that you're going to Chicago Water Week. But we have both spent a lot of money on water quality regionally and locally in the USA, but also still have pretty big issues. So over $2 trillion has been spent since the passage of the Clean Water Act and the Safe Drinking Water Act. And we now find ourselves in a setting where only about 50% of watersheds in the United States are found to have met the Clean Water Act standards of fishable, swimmable, and drinkable. So there's likely a lot more spending to come, I think, is part of the context that we need to make sure you know. And a lot of that spending is going to be on things like the bottom right picture, algae blooms, other things that are oftentimes not only a result from discharged water from treatment facilities, but also just how agriculture, forestry, and development happens in America. And oftentimes in many watersheds, it's actually the biggest amount of in-stream degradation is coming from agriculture, forestry, stormwater runoff kind of outside of cities. And that's what's leading to temperature impairments, algae blooms, phosphorus, nitrogen, sediments, et cetera. A lot of these naturally derived pollutants that are coming off of the landscape. And so that's what provides the opportunity for looking at carbon. So the gray infrastructure solutions, large technology solutions have been the status quo, and it's been a very good status quo. I think we've done a lot. We've done very well compared to other nations in terms of providing clean drinking water to our citizens, as well as improving in-stream water quality conditions over the last many decades, since the 1960s or 1970s. Some of you may know that, we used to have a problem with rivers catching on fire because of untreated pollution, and those things thankfully no longer happen. However, all of that use of technology has an energy impact. And so 4% currently of US annual energy use goes to water treatment and conveyance. And, per year, that $2 trillion works out to around 30 billion, although some years it's much, much more. And just looking at the tonnage of carbon emissions, it's a quite large number. When you look at sources from the United States, there's quite a bit of greenhouse gas emissions that are directly attributable to the US water sector. Now, the US water sector for a couple of decades at least has also seen value in what are called watershed programs, nature-based solutions, natural infrastructure, green infrastructure. There's kind of a range of descriptions for these solutions, but essentially looking out to, outside the fence line and finding ways to reduce agricultural runoff, improve forestry health, other ways to reduce, stormwater runoff or flooding that are, mostly planting trees and wetland plants, but also could be cover cropping on agricultural fields, irrigation upgrades, keeping livestock out of rivers, et cetera. So you see here, I don't need to read it all, but you see here that nature-based solutions have obviously water quality benefits, but often many, many other benefits, and they are often carbon neutral or carbon negative, meaning that they suck carbon out of the atmosphere as, a byproduct of their continued existence. So many of you probably know of the 1997 New York watershed example. It's still kind of the biggest one and the one that folks think of. That's allowed New York City to avoid the highest levels of drinking water treatment because they've worked with their watershed to reduce pollutant loading. Water quality trading there on the fourth bullet is a specific term of art, I would say, that EPA has deployed since actually 1986, but formally supported since 2003. That's a way for industrial and wastewater dischargers to basically look to formally pay for a watershed solution in lieu of a facility upgrade. But important to note that it is not used very often. So compared to the 30 billion or so that go into the U.S. water sector, there's much less than $100 million a year that is going into kind of water quality trading, adaptive management, watershed solutions writ large nationally. So it's a very, very small percentage. And looking at that kind of discrepancy is what led Virridy and a couple of other folks to work on what we call the Watershed Carbon methodology, which was just finalized this year. So looking at that methodology, and this is all setting up my colleague Braden in the research that he'll go through here in a couple of minutes. The watershed nature-based and green infrastructure activities, avoiding emissions from water management, gray infrastructure construction, and operations methodology. You'll note in the carbon world, all of these methodologies kind of have lengthy names to make sure it really covers exactly what's happening. But functionally, what this methodology allows and supports now is in that top bullet. It instructs project developers on how to perform a adequate life cycle analysis, which is looking at the carbon impact over time of a facility upgrade, or looking at the carbon impacts over time of a watershed solution that would allow a facility to not have to do the upgrade. And so again, this is looking, this is in the context of the fact that watershed solutions are possible for many wastewater utilities and other dischargers to comply with the Clean Water Act in America. They just are not getting chosen. And we can touch on further reasons why, but broadly, it's because it's much more complex to work with a bunch of private landowners and stakeholders in your watershed versus paying a consulting firm to build a facility upgrade and help you operate it. The regulators, also kind of balk at the complexity there. And so even where watershed solutions are cheaper, oftentimes they're not selected just because of kind of the complexity and the natural inertia of the U.S. water sector to continue to develop technology solutions for single parameter compliance. So I think that covers a lot of the context. We are lucky at Virridy to have great university partners, and one of them is Braden Lim, who I will pass over the hosting duties to. Braden recently had an article published in Nature Communications, which took the methodology that was published in January and applied it at a high level to all of the United States to get some idea of how many carbon benefits could be generated, how many infrastructure upgrades could be avoided, and has some pretty striking results. So I'll pass it over to Braden. And again, thank you for your questions in the chat. We will get to that in the Q&A at the end of this presentation. All right, let me pass over to Braden. All right, Braden, you are now the host.
Perfect. Is that coming through all right?
Yes.
Okay, thanks, Alex, for the great introduction. So I'm Braden Lim. I'm a researcher at Colorado State University working with Dr. Jason Quinn. My focus is kind of these geospatial analysis, focusing on the taxonomic assessments and life cycle analysis of carbon reduction technologies in general. So I'm going to go over the methodology and results that we got from this paper that was recently published, as Alex mentioned. So this is really just a high-level analysis of the U.S. at large, and I'd say more detailed studies need to be done, but it gives us an idea of what the potential impact of these different water quality trading programs can have. And so, as Alex mentioned, a huge problem right now is increased nutrient loads in our waterways. For this study, we focused primarily on agricultural runoff and specifically nitrogen and phosphorus. And so on the right here, we have maps of how specifically the Mississippi River region has very high nitrogen and phosphorus runoff into it from the Corn Belt and agricultural use in those regions. And so right now, or I'd say in general, there's two ways to treat increased nutrient loading in these rivers. The first is traditional, or what we call gray wastewater treatment. It's just a single site wastewater treatment facility. You can either upgrade these facilities or build new facilities to meet increasing nutrient loads. They are energy intensive and capital intensive, mainly due to the large electricity and energy requirements that they use associated with them. The alternative to that is more nature-based, or what we call green water treatment options. And so these are treatments that are applied at the farm level, at the agricultural level, to minimize the nutrient runoff into those waterways. And so examples of this are smart fertilizer application, so using the correct amount of fertilizer instead of just applying a bunch on the field, using cover cropping, no-till agriculture, on the farm itself, but also doing some filtration methods at the interface between the waterway and the field. So you have increasing the riparian buffers and filtering the runoff through those, or using other filtration methods can actually reduce this nutrient loading before it enters the waterways. And so this analysis is looking at if we take all of the wastewater plants in the US. So we pulled data from the EPA and their water pollutant loading data set for almost 30,000 water treatment facilities in the US. This data set provides how much nitrogen and phosphorus these plants are discharging, how much water they're discharging, and their geospatial coordinates, so we can know where they are and what regions we can do trading within to hopefully offset increasing nutrient loading with these green infrastructure methods. The EPA, to do this analysis as a whole, there's not one blanket treatment level that's required for plants today. There was a great study done by the EPA looking at what the increased gray infrastructure cost would be if nutrient concentration regulation was increased. And so I have 4 of the 5 levels here that they used in their study. The first level was actually no concentration limit, which wasn't very helpful. So we're using levels 2 through 5 here. The results that I'll show today are focused on level 5 results. So this is every wastewater facility needs to discharge their water with nitrogen concentrations no greater than 2 milligrams of nitrogen per liter and no greater than 0.02 milligrams of phosphorus per liter. So pretty strict concentrations, but again, we did this analysis for all of these levels and those results are in the publication. And so the question here was, if we took a Huck 6 subbasin water region and said the wastewater facility is in this region, is there agricultural land within that region that we can do nutrient treatment on, and so we don't have to do the upgrades to the plant is the premise of this study. And so to do this, I have this flow diagram, which isn't the most fun to walk through, so I'll try and breeze through some of the methods here, and happy to answer any questions at the end or offline if those come up. But the primary thing was to evaluate what increased infrastructure would be needed to meet these new nutrient targets and how much we could actually treat with the green treatment methods. So the first thing to do with this study is take the gray treatment methods from that EPA report I mentioned, also take green treatment methods from the literature. Most of this is done in the Corn Belt, update the cost of those so that they're on the same playing field. We then updated all of the electricity costs and electricity emissions for the gray treatment facilities based on their geographic location to try and tease out the areas that had high emission electricity or high cost electricity. We did something similar with the green treatment methods. We assigned life cycle inventory data to the green treatment methods to estimate their environmental impact as well. And then once we had those initial inputs identified, we were able to do the analysis and identify, we take each green treatment method, so smart fertilizer applications, no-till agriculture, cover crops, barrier methods, filtration methods going to the waterways. We looked at how much agricultural land is available in each of these HUC6 regions, how much nutrient load is currently being released from that land on a per land area basis, the existing green treatment prevalence there. So some areas are already doing no-till or doing cover crops. We had to take that into account. And then availabilities, if they had a riparian buffer, how they discharge their water to the stream was also taken into account. The benefit of these green treatment technologies is they can be used in combination. You can do smart fertilizer application and do cover cropping. And so we did combinations of all of these as well. And with that, we were able to calculate the total possible nutrient load that we could reduce with green treatment technologies based on the agricultural land availability in the HUC6 regions. The last thing we had to do is take that EPA data for all of the wastewater treatment plants that I mentioned earlier, add the EPA nutrient treatment targets, and calculate how much nutrient load reduction was required to meet these concentration limits. And then the last thing was to take the maximum treatment possible or the maximum treatment based on green technologies driven by their land limitations. So we took the maximum there. So we either treated all the way down to the concentration limit or treated to the maximum based on the agricultural land we had available. And then we used those nutrient reduction targets or nutrient load reductions for both gray and green. So they were compared on an even baseline and calculated the total cost and total emissions to meet those treatment targets. And so across the US, the left plot here shows how much nitrogen we could treat within each HUC6 sub-basin, and on the right, how much phosphorus we could treat. And so at a national level, meeting the level 5 of the strictest concentration limits, we could treat 32% of the nitrogen and 21% of the phosphorus across the US. The areas I'll point out are kind of this Northeast. We're limited based on agricultural land. Those are very dense areas and don't have a lot of agricultural land to apply these methods. In the center of the US, there's high wastewater discharge. And so there's just too much discharge for us to treat based on that agricultural land in those regions. And then out west, we have low nutrient runoff from the land on a per area basis. And so we had to implement a lot of green treatment to actually satisfy the demands in those regions. And so those are the key ones that we couldn't treat as much as we would have liked just due to land limitations or high water flow rates in those regions. So from all of that, we can then compare the costs and emissions of gray versus green infrastructure, again, at the same nutrient treatment. And so this is the emissions for gray on the far left, green in the middle, and then the difference between them on the far right. And so retrofitting or building new gray infrastructure to meet these concentration limits would result in about 30 million tons of CO2 equivalent emissions emitted annually. Whereas with the green treatment methods, we actually will sequester about 4 million tons of CO2 equivalent per year. And that's primarily driven due to fertilizer reduction. A lot of agricultural land right now, they just spray as much fertilizer as they want because it's better to over fertilize than to under fertilize. And so with smart fertilizer applications, you can apply the right amount instead of applying extra. And those fertilizers have a lot of emissions associated with them. So in these scenarios, we are avoiding emissions in those regions. And so you can see on the right, total emission savings from going from gray to green would be about 34 million tons of CO2 annually across the US as a whole. In terms of costs, to build new gray infrastructure and pay for the operation costs associated with that, the gray treatment facilities would cost about $29 billion per year to operate to meet these nutrient concentration limits. The green treatment costs would be just under $14 billion per year, and that's due to both the cost of the technologies themselves, but then we also assumed we're paying the farmers to implement these on their fields, so we can avoid that gray infrastructure downstream. And so the figure on the right here is kind of one of the key ones from the study, is the cost difference between the gray and the green infrastructures. What we see is in the east, mainly in the Corn Belt region where there's a lot of agricultural land with high nutrient runoff, there's a huge cost difference between implementing these green treatment methods. They can treat a lot of the nutrients, and so we can save a lot of money. Whereas out west, there's less nutrient runoff on a per land area, and so we have to implement more green treatment technologies and actually increase the costs so that they're slightly greater than the gray treatment costs in those regions. And then the last thing here is just taking it to the carbon financing potential that Alex was mentioning. And so we can say we're saving about 34 million tons of CO2 annually. We assumed a $20 per ton carbon credit cost. And so that allows us to get carbon financing of about $680 million annually just by avoiding those emissions from the gray infrastructure. And so in total, the cost savings here is about $15.6 billion by implementing these green treatment methods. And as I mentioned before, I think this is kind of a first order of analysis. We were really data limited, specifically in like the Western geographic region. Some of these green treatment methods are not really being researched there. And so we had to rely on data from the Corn Belt and apply them to other regions. But the areas that seem to have the biggest potential are also the regions that we have the highest data resolution for. And so additional case studies need to be done here, but this work just shows the promising potential that green infrastructure and water quality trading can have overall compared to implementing more gray treatment infrastructure in the US. So that's all I have to present today. I'll hand it back over to Alex. I have a QR code if you want to scan that to see the publication, or feel free to send me an email on it. I'd be happy to send that over to you. Alex, back to you.
Great. Thank you, Braden. If you can click on my face and give me presenter capacity back on the top right there, and I will share my screen. All right. And are you seeing that?
Yep, looks good.
All right, back where we started. So just another couple minutes, and then if there are any questions, we'd be happy to answer them. So Virridy is a carbon credit project developer, as well as doing water quality and water quantity monitoring. And so we are already, we actually have 6 different wastewater utilities that are already on contract with us, where we are performing these life cycle analyses. And we have a fair bit of funding, especially for a private company. We've been fortunate enough to get a lot of support from the Moore Foundation, the Walton Foundation, and the National Science Foundation to support the development of this concept. The Walton Foundation in particular is funding this webinar, I would say, because they would love us to spread the word and brief folks, especially out in Mississippi main stem states where there are big nutrient issues that may get solved with gray infrastructure, but may alternatively be solved with green. So just quickly through the planning steps, this is not dissimilar to an options analysis for any compliance upgrade at a regulated entity. So, but it's got a carbon overlay. So from a carbon perspective, it's a lot of looking at what is the status quo technology upgrade that one would build, what is the alternative, contrast those two, and then from that have, if the facility chooses, the facility can select the green infrastructure, which would start a credit generation cycle. So in terms of the credit generation cycle, what Virridy is looking to help utilities with is documenting, that life cycle analysis that demonstrates the carbon benefits, obviously documenting the watershed solution such that it is compliance grade so that they will receive Clean Water Act or support from their local regulators. And then obviously the utility needs to move to implement the watershed alternative. And as it does so every year, the avoidance of the technology solution is what generates every year carbon credits. Now, we don't have any examples where the carbon credits will fully pay for the green infrastructure. So that's why we call it more of a catalyst. Even if it can pay for 10, 15% of total cost, we think it would be very impactful in modifying some of the future decisions of water quality treatment facilities in the U.S. And then, I think monitoring is a key point here. As a monitoring and reporting company as well, we've got a number of new monitoring devices put into places like the Yampa River, shown here, where we are demonstrating status quo water quality. And then once the utility starts putting conservation actions on the ground, we will be demonstrating that water quality improvements are happening, or adapting the program if they're not happening at the scale that's needed for compliance. And, I think this is probably pretty logical for folks, but as opposed to a technology solution that's focused on usually a single parameter, nature-based solutions have a lot of what are called co-benefits, and some of those are listed here. Certainly reduced ratepayer cost and, a lot of local jobs, public health improvements from a much longer section of river being having healthier water quality conditions. And obviously a lot of these are stream bank plantings, wetlands, various agricultural efficiency upgrades, which have overall aesthetic benefits and air quality and biodiversity, you name it. And that is what we're excited to share with you all. If there are any questions, go ahead and take yourself off mute, introduce yourself and ask, or you can fire them into the chat. We'd love to answer any questions for the next 5-10 minutes. Thank you. Just looking and seeing if anybody has the interest. Rania? Nope. Okay, seeing none. We would really thank you all for your participation. Again, happy Chicago Water Week. We hope to be there in person next year, and ideally with some case studies on how this methodology could be applied in Illinois or in some of the neighboring states. And yeah, we're excited to continue to develop this. Thanks again, and take care.